Hi guys, in this video I'll be talking about the true nature and beauty of Newton's first law and its true uses. Okay, first let's talk about four main interpretations of Newton's first law. The first one is the one all of us know. The fact that, okay, it's the fundamental property of the universe that if a body is moving with some velocity, it will continue to do so until and unless a net force acts on it. Okay, all of us know this. Let's just quickly proceed to the second interpretation. The second interpretation says, okay, from the first statement, we can conclude, okay, from here I can define what a force is. A force is something or an action that changes the state of motion of an object. And this is a better way of saying it. These two interpretations give us a lot of useful information. Yeah, okay. Third interpretation we can say is, okay, fine. From here I can define a term called inertia. Okay, I'm defining a term called inertia, and this inertia is the tendency for every object with mass to resist a change in its state of motion. I can define a term called inertia like this. And what is the use of defining inertia like this? We can give a reason to which y forces are required. We say, okay, there's a fundamental property of all objects with mass that they will try to resist a change in the state of motion. That is why if we want to change the state of motion of an object, we need to apply forces. So the third interpretation gives a reason behind the second interpretation, and all these three interpretations combined give us a very good idea about what Newton's first law is about. But you might be thinking, okay, all of this is great, except in Newton's second law, he literally defined what a force is. He said force is something that causes a change in momentum, and force is defined as the rate of change of momentum, which is simple, obvious, it defines a force. What was the point of defining it in the first one at all? And taking a special case saying, okay, if the force is zero, then the velocity is constant. It's like saying his first law was a special case of the second law. So what was the point of the first law at all? First law was saying if force is zero, velocity is constant. And second law is saying, okay, force is ma. And if force is zero, acceleration is zero. So second law is much more useful in the first law and also includes the first law. So what was the true use of first law? That's what I'm going to tell you in this video. Continue watching. The last interpretation, the fourth interpretation, is the most useful interpretation of Newton's first law. What does it state? It gives us the identifying rule to which we can identify what is an inertial frame. What is an inertial frame? An inertial frame is such a frame where if you are to go into that frame, then all your observations and your predictions using Newton's laws will not contradict each other. That is to say, a frame where you can apply Newton's laws is an inertial frame. Now, not all frames are inertial. That is to say one person is standing at rest with respect to the earth and you're accelerating at 5 meters per second. Then you look at him and he is accelerating 5 meters per second behind. So if you observe using forces, there is no net force acting on him, but he's accelerating. So Newton's laws are not applicable in this frame. So this frame is not inertial frame. So what is the identifying rule for whether a frame is inertial or non-inertial? Well, if the net force on a body is zero, and in a frame you observe that the body is moving with constant velocity, then the frame is inertial. And in that frame, you can apply Newton's laws. So this is the crux of Newton's first law. It says, okay, I can give you the frame where you can apply Newton's laws. I can give you the frame where you can apply F equals to ma. And that is Newton's first law. Okay, so now I've told you all interpretations of Newton's first law. Let's go into misinterpretations of Newton's first law. So there are two misinterpretations that I would like to talk about. The first misinterpretation is very common and is very easy to explain. The second one will take a bit more time. Okay. So the first misinterpretation of Newton's first law is that it does not apply to real life, because when we see an object moving with constant velocity, it seems to stop by itself. I have never seen something moving with constant velocity unless it applies a force in the direction of its motion. That is to say, if I slide a book on the table, it comes to stop by itself. I'm not applying any forces, it's coming to stop by itself. A car is moving on the road with constant velocity. It still has to press the accelerator a bit, because otherwise, if you don't, it's going to stop after some time. Well, this is not exactly true. Some people think Newton's first law is not applicable in real life or something like that. That is wrong, because actually in reality, friction is everywhere. You can't stop it. No matter how smooth the surface is, there's always going to be some friction. And friction is the force that causes net force, which causes deceleration or acceleration depending on which direction it is acting. So that's pretty easy to explain. Friction always is exerted on an object and it may stop an object, which is why it appears that Newton's laws are not applicable in real life, but they are applicable, and even Newton's laws apply for friction as well. If you want an object to move with constant velocity with friction, then you need to make the net force zero, means you need to apply a force against friction to make the net force zero. Okay. Next, the second misinterpretation, which is very deep and it would take some time to explain. The second misinterpretation of Newton's first law is that there exists something known as an inertial force. What is an inertial force? Remember, I told you inertia is the tendency of an object to resist a change in its state of motion. So when you hear the word resist, you might think of a resisting force, like friction, say. So if I were to take something and accelerate it, then there will be an inertial force acting in the backward direction that is caused because of the inertia of the object. Such a force does not exist. Let me give some examples about some inertial forces. So let's say you're on a plane and the plane is about to take off. So you feel as if you're being pressed against the chair when the plane is about to take off. Who is applying this force on you? You don't know. And we call this an inertial force because people think it is because of their inertia that they're experiencing this force. Another example of inertial forces is centrifugal force. When you're rounding a corner with a car or something, you're thrusted against the side of the car. Who's pushing you? You don't know. But you call this an inertial force because it is caused by the inertia of you. Say if you when you're in a car, you wish to go in a straight line. But when you're rounding a corner, you're accelerating towards the center. And according to people, they think that because of inertia, there will be a force in the opposite direction. That is what we call centrifugal force. And this is quite intuitive, like I said in the two examples. But what I'm telling you is inertial forces don't exist. Okay, let me elaborate about how to find whether a force exists or it doesn't. If you want to know whether a force exists or it doesn't, you need to know whether you can find who is the agent of the force, who is applying the force. When you have normal forces, you know the table is applying it, or you know the object in contact is applying it. But do you know the agent of these inertial forces, so called? No, you don't. Do you know who's throwing you to the side of the car? No, you don't. Do you know who's pressing you to the back of the seat? No, you don't. So this can't be a force because forces have agents. And if there is a force, there must be a reaction force as well, where you are applying a force on the agent. So there cannot be such a force which is applied by no one. Okay, so now I've told you what a real force is. Let's talk about some fake forces. Okay, remember I told you about inertial and non-inertial frames when in the fourth interpretation of Newton's first law? Well, in non-inertial frames, if you want to apply Newton's laws, you need to do some extra work. Okay. What extra work do you need to do? You need to apply these things called pseudo forces or fake forces. That is what you do when you're in a non-inertial frame. Let's say it's easy to solve a question when you're in a non-inertial frame. So you want to apply Newton's laws in a non-inertial frame. What do? You apply these imaginary forces to the object that help you in applying these laws. Now these forces don't exist really, you just put them from your brain just to be able to apply laws. These forces don't are not exerted on the object in reality. Hence, we cannot say that the body is experiencing a pseudo force. No, pseudo forces don't exist. Like the name, pseudo force, fake force, false force, fictitious force. Okay, so that is what pseudo forces are. They're fake forces that we apply on objects in order to apply Newton's laws. Okay, now let me connect the pseudo forces and inertial forces. So one might say, if you're in a plane, you're in an accelerating frame. So if you're making observations sitting inside the plane, you need to apply pseudo forces. And the reason you're feeling a backward force is because of the pseudo force. One might say this. One might also say, okay, I'm looking at a tree outside, I'm looking at the tree and the tree is accelerating backwards. That is because the tree is experiencing pseudo forces. Okay, fine. That's what you say. What I'm saying is pseudo forces don't exist in reality. There is no real force acting on the tree. There is no real force acting on you. But you are feeling as if you're being pushed behind and the tree looks like it's accelerating behind. The reality is if you're trying to make conclusions in a non-inertial frame, then you apply pseudo forces. The tree will not break if the pseudo force is large enough. Pseudo forces are just applied by our brain to be able to make conclusions. If you say you're experiencing a pseudo force, that's wrong because you can't experience a fake force. If you're experiencing a force, that means that force is real. You can't experience fake forces. Okay, so now let me explain why we feel forces even though they don't exist. So let me start explaining about what exactly do we feel. Okay, do we feel external forces or do we feel internal forces or do we feel external pressure, internal tension? What exactly do we feel? Okay, let's just take the example of weightlessness. When you're weightless, you feel as if there is no force acting on you. Your your hands are flying around and there's nothing, there's no force acting on you at all. You're at rest. You feel as if like you're at that. Okay. But when you're standing on the ground, do you feel weightless? No. You feel as if someone's pulling you down. Now you think assume that that is gravity. Gravity is pulling me down. That's why I'm feeling this weight. But when you jump out of the window, you feel weightless. Gravity is still pulling you down. Why is it that you're not feeling that force? So I'm trying to bring this question, what exactly do we feel? Do we feel external forces, internal tension, or do we feel something else entirely? So the point I'm trying to bring is a human body experiences internal forces and not external. Okay, let me elaborate. When you're standing on the floor, we can assume the human body is made of many layers. Okay, the bottom layer is stopped by the ground. The ground is exerting a normal and the earth is attracting by gravity. Okay, the last layer, the layer closest to the surface is at rest. But the rest of the body is piled up on top of that layer and the rest of the body wants to go down. So what should the bottom layer do? The bottom layer has to push the next layer upwards and so on. The second layer needs to push the third layer upwards and it needs to push the closest layer downwards. Same thing continues up and up to the top. So are we actually feeling the gravity force or those layers pressing against each other? The answer is we're feeling those layers pressing against each other. If you don't believe me, then we'll take the example of jumping out of the window. You feel weightless. MG is still pushing you down. What is not there? Normal. What is normal doing? Stopping the bottom layer. And if you're jumping out, there is nothing stopping the bottom layer, nothing stopping the second layer, third layer, nothing. There's absolutely nothing. Everything is falling down at the same rate. And if everything is falling at the same rate, what is it? What is the only thing that is changing? One, there is no pressure between, there is no forces between those layers and we're experiencing weightlessness. Weightlessness means what? No force is acting on us. So we are experiencing that there is absolutely no force acting on us. And what is the only thing that is changing when you're out, when you're jumping out of the window and you're standing on the ground? Compression. Compression between those layers. So what I'm trying to say is we don't experience external forces, we experience internal compression between the layers of our body. We can also apply the same thing to you in an aeroplane. When you're in an aeroplane, the airplane is accelerating forward. Okay, so we can now consider vertical sections, vertical layers. Okay, the back of your body is accelerating with the plane due to the force exerted by the plane's seat. You're not feeling that force because that's only on one layer. Okay, now the last layer is pushing the next layer, and the second layer is pushing the third layer, and the third layer is pushing the fourth layer, and so on. So what's actually happening is all your layers were separated by some certain distance, and then when the plane starts accelerating, this layer comes and hits this layer. It's like this layer comes and hits the next layer, next layer, and all of those layers start coming closer together, and all the gaps between them have been reduced by some amount. Now we feeling the force in backward direction is because of this layer compression. If you are initially this, if the layer the border layers were initially at this distance, now they're at this distance because all the gaps in them have been decreased. So that is exactly what you're feeling. You're not feeling an external force of the seat pushing you forward. You are feeling a net backward force. And what you feel is not external forces, what you feel is internal tension and forces. You are feeling layers of your body pressing against each other. You're not feeling external forces. Let me take some other examples if you don't believe me until now. Consider you taking a U-turn in a car. Okay, so you are at the side of the car, and when you're taking a turn, the molecules of atoms, one layer of skin is being pushed by the side of the car, and that layer is being pushed. Not no other layers are being pushed directly by the car. So what's happening now? Again, you're taking vertical strips. Okay, now so the last layer is being accelerated by the car's side door, and the rest of the layers, what happens is they are due to inertia, they are going to try to stay in the same path only. But then when you're taking a turn, this layer is coming like this, so this is going to eventually hit, and when they hit, this is called compression, which is why you suddenly get squeezed and you feel as if you're going towards the door. But why are you feeling as if there's a force towards away from the center of the rotation of your car? That is because due to your layers of skin coming, layers of your body coming closer and closer to each other, it feels as if you're being pushed to one side. It feels as if you're not going towards the door, but the door is coming towards you. It feels as if someone is pushing your other shoulder and making you come closer to the door. These vertical strips are coming closer. So why is it that this doesn't happen for all external forces? If you truly want to know whether you're feeling external forces or internal forces, you have to consider a force which acts at every layer of your skin equally. And what is that awesome force that acts on each of your particles individually? That is, again, like I've already mentioned, it's gravity. Gravity acts at each particle. So when you're jumping out of the window, what's actually happening is gravity is making all your particles accelerate at the same rate downwards, and there is no relative motion between them. There is no deformation happening. No one is trying to squeeze the layers together or move them relative to each other. No, there's nothing. The gravity is just making them all accelerate downwards at the same rate. But when you're standing, what's happening is one bottom layer is there, and your natural state is not standing. Your natural state is in free fall, you would say. In free fall. So what's happening is those layers have some area. But when you're standing, those layers get compressed a bit, which is why you're feeling tension when you're standing on the ground. Now, I won't be able to tell you exactly where you're feeling forces because, like I've said, the human body is not very good at judging where exactly we're feeling forces. Okay, so I hope you got my point now. Human body does not feel external forces, And if you want to check that, you really have to observe a force where each the relative motion of all the particles of your body is zero. Then if that force is acting, then that force you won't feel it at all. You feel compression between you feel relative motion between the particles of your body. You don't feel external forces. If external forces cause relative motion between the particles of your body, then you feel something, you feel some tension. Which direction you feel it in, that is all very different than the direction of the real force. Like I've mentioned, in the airplane, you feel as if you're being pushed backwards, even though the real force acting on you is forwards. So things get really crazy when you're talking about direction of the external force, even magnitude of external force. Those all we can't feel. We feel different things. If you're pressing your hand like this force is causing a tendency for relative slipping, you could say. This force is causing the tendency for my hand to go flying off from the rest of my arm. But that's not happening. That's why I feel as if there is some force. I feel some tension. But if there was such a force that applied on all particles of my whole arm, assuming my arm was not attached to my body, then if it attached on all parts of my whole arm, I would not feel the force at all, which is precisely what gravity does. I don't know if there are any other forces which apply on each particle. I guess you could say electrostatic repulsion and attraction if I was a charged body or something like that, but I'm not charged. Or maybe I am. I don't really know. It's not effective enough. I can't feel electrostatic attraction or repulsion, but gravity I can feel when I'm standing. I feel as if someone's pushing me down when I'm standing, but when I jump out, I don't feel any attraction or repulsion, nothing. Okay, so now the final conclusion of everything, we know that we until now we thought that we experience external forces. Why? Because there are infinite examples of us experiencing external forces. There's an external force and we're experiencing something. There's an external force, there are infinite examples of external forces that we are experiencing some tension or something like that. There is only a few examples where an external force does not cause tension. And that is one example that says that okay, you don't experience external forces, you actually experience tension. So what I'm trying to say is infinite examples may be in support of your theory, but if one example is not, then the theory is wrong. For in infinite examples, the force caused some tension and it was the tension that you are feeling. But in one example, the force did not cause any tension and you did not feel anything. And then you realized, oh, it's not the force that's causing this experience, it's the tension that's causing this. So I don't know if my theory is right. I have a few examples where the force is not causing tension, but it may be possible that actually what we're experiencing is not tension, not force, something else. And that is my challenge to all of you. I want you, because I have said a few examples in support of my theory, and I'm not sure whether it's right or wrong because I have only a few examples. Even if I had infinite examples, I would not be 100% sure that this is right. This is right. So that is the challenge. You have to find one case where this tension, what I'm saying is we experience internal tension and not external forces is wrong. And then you can say that, okay, what I'm saying is wrong. Okay, thank you. Bye.